Hey guys, for our 152 final project, our group did an FEA analysis on a RC race car. Our team members are Huynh, Thi Anh Tran, Pham, and Thi Anh Tran. So here's a top view of our RC car, and shown next to it are the properties for high-density polyethylene, which is going to be the material of our RC car that we're going to be using. For our studies, we ran analyses of our control arm and chassis along with different design iterations to determine which design is the most optimal. Starting off with a standard analysis of our control arm, we ran a static analysis from a brake load, static analysis from varying weight loads, frequency analysis, and buckling analysis from compressive loads, with the boundary conditions given below. The values displayed are the results that we will be using to compare with our various iterations. We also conducted a fatigue analysis of the control arm. When the max stress in the control arm reaches 13 megapascals, the arm is expected to reach 200,000 cycles until failure. The plot shown is obtained from fatigue damage experiments and modeling of high-density polyethylene. For every 30 minutes of playtime, the arm is predicted to go through 1,000 cycles. If the arm is used twice per week, the arms are expected to have a fatigue life of nearly 2 years. For our first iteration of our control arm, we changed our material from high-density polyethylene to 1060 alloy, which gave us a usable yield strength and extended our control arm by 20 millimeters. Comparing our new results to our old results of our static and frequency analysis, we saw that our max von Mises stress and resonant frequencies increased. This made sense because looking at our equation, by increasing the length, we are increasing the distance from our centroid. Looking at our results, our control arm did not fail. Continuing off of this iteration, we had increased the brake load from 2.5 newtons to 10 newtons. Our results showed us that the max von Mises stress nearly doubled. Though our max von Mises stress was barely higher than our yield strength, our control arm failed regardlessly. Zooming in onto our fixed location, we could see where it had failed. This indicated that we could apply a brake load of up to a little bit under 10 newtons before the model would fail. Looking at the buckling analysis, our buckling occurred at the same location. For our second iteration, keeping the same boundary conditions as before, we had instead reduced our thickness by half. Looking at our max von Mises stress again, we saw that it was a little bit higher than our yield strength, which meant failure. This indicated that we could reduce the thickness of our arm up until about half of its original thickness before it would yield. Next, we ran a study for our chassis. We did a static analysis of hardware loads, static analysis of various stepping loads, frequency analysis, and a thermal analysis from an overheating battery. Similar as before, we will be using these results to compare with the results from our iterations. Using our closed-form equations, we got different results from our SOLIDWORKS analysis. From our SOLIDWORKS results, we got 0.37 inches in max displacement compared to 0.149 inches in the equation. This is due to the oversimplification from the closed-form equations. We imagined the chassis as a beam with a hollow rectangular face, but in actuality, the chassis has an open face. This caused the SOLIDWORKS results to give a higher displacement than the equations. For our first iteration of the chassis, we added more slot cuts to the part of the chassis that held the battery for increased cooling. In this study, we used heat coefficients of 1, 20, and 40. For heat coefficients of 20 and 40, we saw that the max temperature had decreased from our original design. However, for heat coefficients of 1, max temperature actually increased. This is because there's less material, so less cooling in the conduction. For our second iteration, using the same boundary conditions as before, we increased the thickness of the chassis. This made the chassis more resistant to yielding and buckling with little change in the effectiveness of cooling. In conclusion, from our studies, we saw that the optimal design would require us to decrease the thickness of both the control arm and the chassis, and increase the slot cuts within the chassis. Thank you for watching, and hope you guys enjoyed the video.